welcome to this problem walkthrough. Today, we'll explore LeetCode problem number 233, titled Number of Digit 1. In this problem, we aim to calculate how many times the digit 1 appears in numbers from 1 to n. We'll break down the approaches, discuss complexities, and learn key takeaways. Let's get started. In this problem, we are tasked with counting how many times the digit 1 appears across all numbers from 1 to a given integer n, inclusive. This means we need to consider every occurrence of 1, whether it's in the units place, tens place, hundreds place, or any other position. For example, if n is 13, we would count the 1 in numbers like 1, 10, 11, 12, and 13. The input is a single integer, n, which can range from 1 to 2 billion. The output will be a single integer representing the total number of times the digit 1 appears in this range. Let's consider an example where n equals 13. The numbers from 1 to 13 are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. Now, if we count the occurrences of the digit 1, we see it appears in several places. It shows up once in the number 1, once in the number 10, twice in the number 11, once in the number 12, and once in the number 13. Adding these together, we find the total count of ones is 6. Now, let's look at another example where n equals 20. The numbers from 1 to 20 are listed, and we again count all the appearances of the digit 1. It shows up once in the number 1, once in the number 10, twice in the number 11, and then once in each of the numbers 12, 13, 14, 15, 16, 17, 18, and 19. Altogether, the digit 1 appears 12 times in this range. For a larger example, let's take n equal to 100. Here, the range spans from 1 to 100, and we need to count all occurrences of 1. In the numbers 1 through 9, the digit 1 appears only in the number 1. From 10 to 19, 1 appears 11 times, once in each number. From 20 to 99, 1 appears in the tens place every 10 numbers, such as in 10, 11, and so on up to 19. Finally, in the number 100, 1 appears once in the hundreds place. Summing these, the total number of ones is 21. To summarize, the total count for n equals 100 is 21. This problem also comes with a few constraints. The value of n can be as small as 1 or as large as 2 billion, so our solution must be efficient enough to handle such large inputs. Edge cases include scenarios like n equal to 1, where the count is simply 1, or single-digit numbers like 5, where the count is determined by whether 1 is included. For larger numbers, we must account for all positional places where 1 can appear, such as in the units, tens, hundreds, and beyond. A naive approach of iterating through all numbers would be too slow for very large n, so an optimized solution is necessary to meet the performance requirements. To solve LeetCode problem number 233, which asks us to count how many times the digit 1 appears in the range, 1 int n, we need to consider the efficiency of our approach, especially for very large values of n. The first approach we might think of is brute force. The idea here is straightforward: iterate through every number from 1 to n, and for each number, count the occurrences of the digit 1. This can be done by either converting each number to a string and using built-in functions to check for 1, or by using mathematical operations like division and modulo to extract and count digits. While simple to implement, this method has a significant drawback: it's inefficient for large inputs. The time complexity is O, n*d, where d is the average number of digits in the numbers. For large n, like 10 to the power of 9, this quickly becomes impractical. To address this inefficiency, we can turn to a more optimized approach: digit position analysis. Instead of checking each number individually, we analyze how the digit 1 contributes at each place value: ones, tens, hundreds, and so on. By breaking the number into higher, current, and lower parts, we can calculate the occurrences of 1 for each digit position using modular arithmetic, achieving far greater efficiency. Now, let's break this idea down further. Consider how the digit 1 appears in specific ranges. For example, between 1 and 99, the digit 1 appears 10 times in the tens place, specifically in the numbers 10 through 19. Similarly, it appears 10 times in the ones place: 1, 11, 21, and so on. This pattern can be generalized for any digit position. To do this, we analyze the number n by dividing it into 3 parts: the digits higher than the current position, the digit at the current position itself, and the digits lower than the current position. Using this method, we can compute the contributions of 1 at each place value in constant time. This approach has a time complexity of O log 10 n, as we process each digit position once. It also has a space complexity of O 1, making it memory efficient. Additionally, while there are alternative approaches, like a recursive solution that breaks the problem into smaller subproblems, the mathematical approach stands out. Recursion has similar time complexity but requires additional memory for the call stack and can be harder to debug. By focusing on digit-level contributions, the mathematical approach avoids these drawbacks and provides a clear, efficient solution. When comparing the different strategies, the trade-offs become clear. The brute force approach is simple to implement and easy to understand, but it's extremely inefficient for large inputs due to its high time complexity. The recursive approach, on the other hand, is more elegant and avoids iterating through all numbers, but it introduces additional memory overhead and complexity, making it harder to debug. The mathematical approach strikes the best balance. It's highly efficient, with a time complexity of O log 10 n, and avoids unnecessary computations by focusing directly on the contributions of the digit 1 at each place value. This makes it scalable even for very large inputs, such as n equals 10 to the power of 9. Additionally, since the method is iterative, it's easier to implement and debug compared to recursive solutions. Overall, the mathematical approach is the most effective strategy, providing both clarity and performance, which is why we've chosen it to tackle this problem efficiently. To solve LeetCode problem number 233, number of digit 1, the objective is to count how many times the digit 1 appears in all numbers from 1 to n. Given the potential size of n, which can go up to 2 billion, a brute force approach that iterates through every number would be far too slow. Instead, we adopt a mathematical strategy that focuses on analyzing the contribution of the digit 1 at each positional place value, such as the units, tens, hundreds, and so on. By breaking the problem into manageable parts, we can count the occurrences of 1 in each digit position separately using modular arithmetic and integer division. We begin by initializing some variables. Position starts at 1 to represent the current place value, count is set to 0 to accumulate the total count of 1, and current is assigned the value of n, which is the number we're analyzing. This setup allows us to systematically analyze each positional digit of n, starting from the least significant digit and moving leftward. The next step involves iterating over each digit position. While current is greater than 0, we divide n into 3 key parts relative to the current place value. First, higher represents the digits to the left of the current place value, calculated as n / position *10. Next, current _ digit isolates the digit at the current place value using n / position %10. Finally, lower represents the digits to the right of the current place value, determined by n% position. Once these parts are identified, we calculate how many times the digit 1 contributes at this particular position. If the current _ digit is 0, 1 can only appear due to the higher digits, so we add higher asterisk position to the count. If the current _ digit is 1, the contribution comes both from the higher digits and the numbers formed by the lower digits, so we add higher asterisk position plus, lower plus 1, to the count. If the current _ digit is greater than 1, 1 appears due to the higher digits as well as the current digit exceeding 1, so we add higher plus 1 asterisk position to the count. This systematic approach ensures we capture all contributions of the digit 1 at the current place value. After calculating the contribution of 1 for the current position, the algorithm shifts its focus to the next positional place value. This is achieved by multiplying position by 10, which moves us from units to tens, tens to hundreds, and so on. Simultaneously, we reduce the number being analyzed by updating current to current / 10, effectively removing the least significant digit. This process repeats until we've analyzed all positional place values of n. Once the loop concludes, the total count of 1 is stored in the variable count, which is then returned as the final result. The key insights that make this approach efficient include the mathematical decomposition of n into higher, current _ digit, and lower parts, and the realization that the digit 1 contributes independently at each positional place value. Because we process each digit of n exactly once, the algorithm achieves a time complexity of O log 10 n, where the number of digits in n determines the number of iterations. Additionally, the algorithm is space efficient, as it relies solely on primitive variables such as integers to store intermediate results, without requiring any complex data structures. To ensure the algorithm handles all scenarios, we need to consider several edge cases. For small input, like when n equals 0, the output is 0 since there are no numbers in the range 1, 0. For single-digit numbers, such as n less than 10, the algorithm correctly counts the occurrences of 1 based on positional analysis. For large inputs, such as n equal to 2 billion, the logarithmic time complexity ensures the algorithm remains efficient and completes in a reasonable time frame. Boundary cases, like when n contains multiple ones in successive digits such as 1111, are handled seamlessly by summing the contributions of 1 in each positional place value. These considerations ensure the algorithm is robust, efficient, and accurate across all possible input ranges. This Python code efficiently counts the number of times the digit 1 appears in all numbers from 1 to n. The solution avoids a brute force approach by leveraging mathematical analysis. Here's a breakdown. 1. Initialization. The variable count keeps track of the total number of ones. The variable factor represents the current place value, units, tens, hundreds, etc., being processed. 2. While loop. The loop continues as long as factor is less than or equal to n. This ensures all place values up to the most significant digit of n are processed. 3. Decomposing n. Inside the loop, the number n is split into 3 parts. Lower. The digits to the right of the current place value. Current, the digit at the current place value. Higher, the digits to the left of the current place value. This decomposition allows us to calculate the occurrences of 1 at each place value. 4. Counting 1s, based on the value of current. If current is 0, the count increases by higher asterisk factor, all combinations from the higher digits. If current is 1, the count increases by higher asterisk factor plus lower plus 1, including combinations from higher digits and the lower digits. If current is greater than 1, the count increases by higher plus 1 asterisk factor, all combinations from higher digits plus the overflow. 5. Update factor. The factor is multiplied by 10 to move to the next place value. 6. Return result. After processing all place values, count contains the total occurrences of 1. This approach is efficient, as it processes each digit of n in O log n time, making it suitable for large inputs up to 2*10 to the power of 9. This is the Java implementation for LeetCode problem number 233, number of digit 1. It mirrors the logic of the Python solution provided, using Java's type system and syntax. Key differences include explicit type declarations, e.g., long for large values during multiplication, and a class structure with the method countDigit1 to compute the result. The logic iteratively calculates the count of digit 1 for each place value, leveraging modular arithmetic to split the number into higher, current, and lower parts for each factor of 10. To start solving this problem, let's consider the example where the input is 13, and we need to count how many times the digit 1 appears from 1 to 13. First, we initialize our variables. Count is set to 0 to keep track of the total occurrences of the digit 1, and factor is set to 1 to represent the current place value we are analyzing, starting with the ones place. In the first iteration, we calculate 3 components. Lower, which is the remainder when 13 is divided by the current factor, is 0. Current, which is the digit at the current place, is calculated as 3. Higher, which represents the digits to the left of the current place, is 1. Since the current digit is greater than 1, we calculate the contribution of this place by adding higher plus 1 asterisk factor to the count. This gives us an increment of 2, making count equal to 2. Then, we move to the tens place by updating factor to 10. In the second iteration, with factor now equal to 10, we again calculate the 3 components. Lower, the remainder when 13 is divided by 10, is 3. Current, the digit at the tens place, is 1. Higher, which represents digits to the left of the current place, is 0. Since current is exactly 1, we calculate the contribution of this place using the formula higher asterisk factor plus lower plus 1. This adds 4 to count, bringing the total to 6. At this point, we update factor to 100. However, since factor is now greater than n, we terminate the process. The final count of digit 1 in numbers from 1 to 13 is 6. Now, let's analyze a new example with n equal to 100. Again, the goal is to count how many times the digit 1 appears from 1 to 100. We begin by initializing count to 0 and factor to 1. In the first iteration, with factor at the ones place, we calculate lower as 0, current as 0, and higher as 10. Since the current digit is 0, we add higher asterisk factor to count. This adds 10 to count, as there are 10 occurrences of the digit 1 in the ones place of numbers from 1 to 100. We then update factor to 10 to analyze the tens place. In the second iteration, with factor at 10, we calculate lower as 0, current as 0, and higher as 1. Again, since the current digit is 0, we add higher asterisk factor to count. This adds another 10, bringing count to 20. Next, we move to the hundreds place by setting factor to 100. In the third iteration, with factor at 100, we calculate lower as 0, current as 1, and higher as 0. Since the current digit is 1, we add higher asterisk factor plus lower plus 1 to count. This adds 1, making the total count 21. Finally, we update factor to 1000, which is greater than n, so the process terminates. The total count of digit 1 in numbers from 1 to 100 is 21. Next, let's look at the example where n is 55. Our task remains the same, counting how many times the digit 1 appears from 1 to 55. We start with count initialized to 0 and factor at 1. In the first iteration, we calculate lower as 0, current as 5, and higher as 5. Since the current digit is greater than 1, we calculate the contribution using higher plus 1 asterisk factor. This adds 6 to count, as all numbers in the ones place from 1 to 55 contribute 6 ones. We then move to the tens place by updating factor to 10. In the second iteration, with factor now at 10, we calculate lower as 5, current as 5, and higher as 0. Again, since the current digit is greater than 1, we add higher plus 1 asterisk factor to count. This adds 10, making the total count 16. At this point, we update factor to 100. Since factor is now greater than n, the process terminates. The final count of digit 1 in numbers from 1 to 55 is 16. This example highlights the efficiency of the algorithm, which processes each digit of n by considering the lower, current, and higher parts of the number. By doing so, we avoid iterating through all numbers up to n, achieving a time complexity of O log n. To analyze the time complexity of our solution, let's break it down step by step. The algorithm processes the digits of the number n one by one, starting from the least significant to the most significant. If d is the total number of digits in n, the while loop executes exactly d times. Inside each iteration of this loop, we perform several constant time operations, calculating the lower digits using lower equals n, and forward slash factor, asterisk factor, finding the current digit with current equals, and forward slash factor, %10, and determining the higher digits through higher equals n forward slash factor asterisk 10. Additionally, updating the count variable and performing conditional checks are also O1 operations. Since the while loop runs once per digit, the total time complexity becomes OD. Now, since the number of digits d in n is proportional to log 10 n, we can also express the time complexity as O log 10 n. This efficiency comes from directly processing the digits without iterating through the entire range up to n. For the space complexity, the algorithm is highly efficient because it does not use any additional data structures. The only variables we maintain are count, factor, lower, current, and higher, all of which require a constant amount of memory. This means the algorithm's space usage does not grow with the size of the input number n. Therefore, the space complexity is O1. This is particularly advantageous because no matter how large the input number becomes, the memory footprint remains constant, making the approach very scalable. To better understand the efficiency of this solution, let's compare it with a brute force approach. A naive solution would iterate through every number from 1 to n, counting the occurrences of the digit 1 in each number. To extract the digits of any number k, we need O log 10 k operations, and summing this across all numbers from 1 to n results in a time complexity of approximately O n asterisk log 10 n. In contrast, the optimized approach eliminates this range-based iteration entirely by directly calculating the contribution of the digit 1 for each position in n. This reduces the time complexity to O log 10 n, a significant improvement over the brute force method. Moreover, the optimized algorithm maintains O1 space usage, regardless of the size of n. Not only is the optimized approach faster, but it also guarantees consistent performance. Since the algorithm processes each digit of n individually, the best, average, and worst case time complexities all remain O log 10 n, with the space complexity constant at O1. To mathematically validate the time complexity, we note that the number of digits in n is proportional to log 10 n. Since the while loop processes each digit exactly once, the total number of iterations is O log 10 n. Within each iteration, all operations such as computing the lower, current, and higher digits, as well as the conditional checks, are constant time operations, or O1. Therefore, the overall time complexity of the algorithm is the product of the number of iterations and the time per iteration, which simplifies to O log 10 n. This proof underscores the efficiency of the approach, as it directly ties the complexity to the number of digits in the input number rather than its magnitude. When solving this problem, there are a few common mistakes to watch out for. First, attempting a brute force approach where you iterate through all numbers from 1 to n is highly inefficient. This leads to an O(n) time complexity, which becomes impractical for large values of n, such as 10 to the power of 9. Instead, the key is to focus on digit-level analysis and leverage mathematical patterns to optimize your solution. Another mistake is off-by-one errors, where boundary cases like the inclusion of the number 1 are sometimes overlooked. This can easily lead to incorrect results, so it's important to carefully account for all contributions. Additionally, zeros in certain digit positions can be tricky. For example, when the current digit being analyzed is 0, it may affect how ones in lower significance digits are counted. Ignoring this subtlety can result in inaccuracies. Finally, there's the misinterpretation of how higher digits contribute to the count. For instance, with n equals 231, the hundreds place doesn't just depend on its own value, it's also influenced by the digits to the left. Fully understanding how each digit interacts with others is critical to preventing logical errors in your solution. Another issue to be wary of is floating point or integer overflow errors, especially when n is very large. This is particularly relevant in languages like C++ or Java, where improper handling of divisions or floating point arithmetic can lead to rounding errors or overflow. To avoid this, stick to integer arithmetic to ensure precise calculations. Now, from an interview perspective, solving this problem efficiently hinges on recognizing the contribution of each digit place, units, tens, hundreds, and so on, to the overall count of ones. By breaking the problem into smaller subproblems for each digit, you can simplify the logic while showcasing your understanding of patterns and optimization. This is a great opportunity to demonstrate critical optimization thinking, as interviewers value your ability to improve a naive O(n) solution to a logarithmic one. It's also important to handle edge cases effectively, such as when n equals 0 or 1, or when n lies just below or above powers of 10, like 99, 100, or 101. Finally, interviewers might ask you to compare your optimized solution to the brute force approach, so be ready to articulate why the optimized version is superior both in terms of efficiency and scalability. This problem also shares similarities with other digit-based problems, so exploring related problems can deepen your understanding. For instance, LeetCode 400, which involves finding the nth digit in a sequence of integers, requires similar digit-level analysis. LeetCode 43, multiply strings, involves breaking down numbers into digit-level operations, while LeetCode 258, add digits, and LeetCode 306, additive number, also focus on digit manipulation and identifying patterns. When it comes to alternative approaches, the most efficient method remains the math-based digit analysis. This approach directly calculates the contribution of each digit based on its place value, achieving an O log n time complexity. However, it does require a solid grasp of the mathematical relationships between the digits and their contributions. Another option is using dynamic programming to pre-compute results for smaller ranges and reuse them later. While this can work, it's less common for this problem due to its higher memory requirements and added complexity. Lastly, digit recursion is an elegant approach that breaks n into smaller subproblems based on the leading digit. While it can be effective, it demands careful handling of base cases to ensure correctness. Each approach has its trade-offs, so understanding their strengths and weaknesses is key to applying the right one for your needs. Great job! To wrap up, we summarized the efficient mathematical approach to count occurrences of the digit 1 and reviewed its time and space complexity. Remember to focus on digit manipulation techniques for similar problems. Thanks for watching, and don't forget to subscribe for more coding insights. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!